Okay, here's a look at how to solve 3.2, number 46. It says, let R be a non-zero finite commutative ring with no zero divisors. Prove that R is a field. Okay, so the first thing to do is to figure out what you have, and I've taken the liberty of writing down, assume R is non-zero. In other words, it has at least one non-zero element. It's finite. It has only finitely many elements. Multiplication is commutative. It's a ring, so we have addition and multiplication. They follow all the nice rules. And we have no zero divisors. I want to show this is a field. Okay. Now remember, we have this theorem 3.9 in the textbook that says every finite integral domain is a field. Now why would I care about that? Because this property, no zero divisors, that screams integral domain. So if R were an integral domain, by theorem 3.9, R would be a field, and it's nice to tell your reader why, since it is finite. Sound good? Okay, so, well, what does it take to be an integral domain? So we want to show that R is an integral domain, i.e. an integral domain is a commutative ring with an identity element 1 not equal to 0 and no zero divisors. Okay, so we've got commutative, we've got ring, and we've got no zero divisors. So life is looking up. So this is an interesting thing. The big deal is it remains to show that R has a unity 1 that's not equal to 0. Okay, that's what I have to show. Now you might say, Guy, I don't know exactly how to show that it has a 1 without coughing up a 1. Well, here's where we basically say, what do we have? What tools do we have? I have that it's non-zero. So what does that allow me to do? Since R is non-zero, basically that means it has one non-zero element at least. So pick A in R with A not equal to 0. What does it mean that it's finite? Remember, in the proof of 3.9, that's the only place we've dealt with finite things before. Since R is finite, list the elements as A1 to AN. So this is basically claiming two things. That's every element in R, and it's not repeating any element in R. Now, so what did we actually do in the proof of 3.9? We multiplied a non-zero element by every element. Note that the set, you can multiply on the left or right. I'll just multiply on the left for the fun of it. So A times A1, A times A2, up to A times AN has n distinct elements, and this is sort of taking a page from the playbook of theorem 3.9. How do I know that there are n distinct elements? For if not, A times AI equals A times AJ, implying, if you remember, that's A times AI minus A times AJ, which equals 0, right? So this is the trick. This is the game you use when you've got no zero divisors. You set something equal to 0. That's A times AI minus AJ equals 0. Now, no zero divisors. This is non-zero. The product is equal to 0, implying that AI minus AJ equals 0, which implies AI equals AJ. So why can't any two of these be the same? Because if two of these were the same, that means AI equals AJ, and we set the list up to be all distinct, right? So we have n distinct elements. Thus, every single element of R can be described in this list. So since every element of R is in this set, well, what am I looking for? So these are the tools I have. I have some non-zero element and I have a finite list, but what am I really looking for? I'm looking for an identity. So what would an identity do? An identity would be something that would have A times A K equals A for some AK, right? Well, if every single element of R is in this set, and A is an element in R, one of these guys has to equal that. Well, so what's my candidate for the identity? It's AK, right? The identity is supposed to be the thing that you multiply everything by and get itself. Since A times 0 equals 0, which is not equal to A, right? AK can't be 0. Notice that. If AK were 0, this thing would equal A, and the only thing I know about A is it's not 0. So AK is not equal to 0. Why is that useful? Well, because you don't just have to cough up an identity, you have to cough up an identity not equal to 0. So now I have my candidate for my identity. So what does it remain to show? It remains to show, well, I've shown AK as the identity for A, but what about every other element? Let's say for all B in R, that let's say B BAK equals B. If I could show that, then it's truly the identity. We've got commutativity, right? So it doesn't matter which side I've got this on. How on earth do I show that for any element? Well, I sort of have zero divisors, so I'm sort of thinking maybe to myself backwards over here. This is my backwards bubble. If I want to end up with B AK equals B, what if I did B AK minus B equals 0, right? This is how we do zero divisors. What can I multiply this guy by? Well, I can multiply this guy times A, because the only traction I can really get is I can get A times AK just equals A. So let's see what we have here. This is what I know, this is what I want, right? How am I going to get from what I know to what I want? But let's say BAAK equals BA, right? I've just multiplied both sides of this equation by b. This is what I have, that's what I want. I'm trying to get there. Now I'd really like to cancel out an a. Well, once it's an integral domain, I can claim cancellation, but I have to go through sort of the work of cancellation again. I'm going to use subtraction over to the other side. BA AK minus BA equals 0. And now I'm going to factor out an A times BAK minus B equals 0. By no zero divisors, first atrocious spelling error. Okay, so by no zero divisors, A not equal to 0, that's the only thing we know about it, implies that B AK minus B equals 0, which implies that B AK equals B. Therefore, AK is the unity. And that ends our proof.